Okay. Hi everyone, it's really nice to be here today and start off the science talk. So today I'm going to be presenting a study where we used ACCESS-NRI 1.5 to look at meltwater impacts of Antarctica over the 21st century. And this is work that I've undertaken with Mad England. And so the motivation behind this study is that the Southern Ocean surface is observed to freshen over recent decades, and surface freshening is projected to continue over the 21st century, in particular as the Antarctic ice sheet shelf melt accelerates. But Antarctic ice sheets and ice shelves are not currently represented in coupled climate models, and this constitutes a fundamental challenge in projecting 21st century climate change. So this schematic, adapted from Falling et al., shows some of the terms important in the Antarctic mass budget for grounded ice and ice shelves. And if we compare this to the typical representation in CMIP models, we can see that there are a lot of differences. So in the CMIP models, there's a land surface so that the elevation is similar to the ice sheet, but there isn't an ice sheet. There's a fixed maximum depth of snow over Antarctica. And in addition to not having an ice sheet, CMIP models don't have ice shelves or ice shelf cavities. In the CMIP models, precipitation minus evaporation over the Antarctic continent is essentially equal to runoff to the Southern Ocean. So the models are simulating some freshwater fluxes to the Southern Ocean. And over the historical period, this approximately matches observational estimates, but they're not for the right reasons. And importantly, over the 21st century, because they don't have a reservoir of ice to accelerate melt, they can't keep up with the additional freshwater projected to enter the Southern Ocean. This is important because the density stratification in the Southern Ocean is largely controlled by salinity. And so this schematic shows the Southern Ocean mean state. There's cool fresh water at the surface and warm salty water at depth and mixing in between. So when we have increased ice sheet and ice shelf melt, we have a strong surface freshening, leading to a strong stratification. And this reduces the convective overturning and leads to a weak entrainment of warm subsurface waters to the surface. And so this results in a surface cooling as well as a warming at depth. An important study has looked at the influence of Antarctic meltwater over the 21st century. So this study by Bronsaler et al. Applied additional meltwater around the Antarctic margins in a coupled climate model and looked at the end of 21st century anomalies that resulted from this. And so this map shows surface air temperature anomalies, and you can see that there is a global cooling anomaly resulting from the meltwater around Antarctica. And across the Southern Hemisphere extratropics, we're talking about cooling anomalies of about 1 degree. This is really substantial. So it's clear that we really need to understand how meltwater will be changing or impacting climate over the 21st century. But this study is based on only one model, and so the results could be model dependent. It's important to verify these in an additional model. Also, there remains considerable uncertainty in projected Antarctic meltwater amounts, and this is notable because the Bronsaler et al. Study applied meltwater corresponding to the Toronto and Pollard projections, which are largely considered to be the very high end of Antarctic melt. And so it's important to understand what sort of climate impacts might result from a lower amount of meltwater as well. So in this study, we use ACCESS-NRI 1.5 to investigate global climate responses to Antarctic meltwater additions over 2000 to 2100. We choose ACCESS-NRI 1.5 because we need a coupled model for our simulations. We're interested in the ocean, sea ice, and atmosphere responses. And ACCESS-NRI 1.5 was computationally affordable, so we could run the ensemble sizes that we needed. We run 2 ensembles of 5 members each on historical and SSP 5/8 forcings, with additional meltwater added around the Antarctic coast. ACCESS-NRI 1.5 already simulates Antarctic runoff, as I described for the schematic previously. And so this does increase over the 21st century as a result of a warming atmosphere able to hold more moisture and increasing precipitation over the Antarctic continent, but not at the rate of melting ice sheets and shelves. So we take this into account when we're applying meltwater additions around the margins to match ice sheet projections. Our first ensemble of experiments is Antarctic meltwater low. And in this ensemble, we linearly increase meltwater to 1850 gigatons per year by 2100 to make a total of 5,600 gigatons per year of fresh water entering the Southern Ocean, in line with the Golej et al. Study. And our second ensemble is the Antarctic meltwater high, where we linearly increase meltwater around the Antarctic margins to 13,600 gigatons per year by 2100 to make a total of 17,000 gigatons per year of fresh water entering the Southern Ocean. And so this is in line with the Toronto and Pollard projections and comparable to the Bronsaler et al. Study. You can see that there's a big difference in how much additional water we're adding between our two ensembles. We compare our output to the historical and SSP 585 experiments from ACCESS ESM 1.5. And so I'll refer to these as control, but they are control with increasing greenhouse emissions. And at this point, I'd like to take a moment to say thank you to the CLEX CMS team and Teal and Chloe from CSIRO, who helped me with setting up these runs and post-processing the data. So if we now get into the global climate response to the meltwater. So in all of my maps, I'll be showing 20-year averages at the end of the 21st century. And I'll always be showing the meltwater low ensemble anomalies at the top and the meltwater high ensemble anomalies at the bottom. So these are different from the control at the end of the 21st century. So starting off, I'm just showing sea surface salinity anomalies so that you can contrast the amount of fresh water between our two ensembles. You can see that in the meltwater low ensemble, there's a moderate freshening in the Southern Ocean because we're not adding particularly much meltwater. And in our meltwater high ensemble, we've got a really strong freshening across the Southern Ocean. In response to this surface freshening, we see a surface cooling via the mechanism that I described previously. In our meltwater low ensemble, this surface cooling is largely restricted to the Southern Hemisphere extratropics. And it corresponds to about 7% reduction in warming relative to the control over the 21st century. We see a strong cooling in our meltwater high ensemble, which corresponds to a 25% reduction in global warming relative to the control over the 21st century. So this is really substantial. And we also see a significant cooling in the tropics as well. And so our meltwater high ensemble is quite similar to the Bronze Sailor et al. Findings. And so this is an important point here that we're able to recreate their results using a different model. But one of the other key things to note here is the difference between the meltwater low ensemble and the meltwater high ensemble. And so if we want to understand what sort of climate impacts will occur in response to Antarctic meltwater, we really need to constrain future projections of Antarctic meltwater. If we look at anomalies in sea ice concentration, we see that these largely mirror the surface temperature responses. So we see a moderate reduction in sea ice loss in our meltwater low ensemble and a substantial reduction in sea ice loss by the end of the 21st century in our meltwater high ensemble. We also see global changes in precipitation patterns. So these are most obvious in our meltwater high ensemble, where we see a drying across the Southern Ocean and a northward shift in the ITCZ. We see a weaker shift in the ITCZ in our meltwater low ensemble. It's still there, but it's largely lacking regional significance. And so in response to the Antarctic meltwater additions, the Southern Hemisphere cools more than the Northern Hemisphere. And so we increase the interhemispheric temperature difference. And to maintain an energy balance in the atmosphere, precipitation moves to the warmer hemisphere, the Northern Hemisphere. When we compare the spread across our ensemble members, this scatter plot is showing the interhemisphere temperature difference on the x-axis and the interhemispheric precipitation difference on the y-axis. You can see that there's a strong linear relationship across our ensemble members. The control members are shown in orange, meltwater low members are shown in blue, and the meltwater high members are shown in purple. And why this is important is because the amount of meltwater entering the Southern Ocean is largely controlling the Southern Hemisphere cooling and thus the interhemispheric temperature difference. And so if we want to have a good idea about how global precipitation is going to change, we need to understand how much meltwater is entering the Southern Ocean or is projected to enter. And finally, if we look at 2,000 metre temperature anomalies at the end of the 21st century, along with the surface cooling, we have a subsurface warming in response to the surface freshening. In our meltwater low ensemble, the warming of the Southern Ocean is 15% above that projected by global warming alone at the end of the 21st century. In our meltwater high ensemble, we're finding a 40% increase in warming above that projected by global warming at the end of the 21st century. So this is really substantial. You can also see in our meltwater high ensemble significant warming in all ocean regions except for the Arctic. And this happens because in the meltwater high ensemble, there's a shutdown of Antarctic bottom water formation by mid-century due to the excessive surface freshening. So we can see that under our high meltwater ensemble, we have really significant changes to the global abyssal ocean. These are more moderate and restricted in our meltwater low ensemble. So in conclusion, using ACCESS ESM 1.5, our high meltwater simulations produce anomalous surface cooling, hemispheric differences in precipitation, and ocean warming at depth. Around the Antarctic margins, our high meltwater simulations show reduced sea ice loss and a shutdown of Antarctic bottom water formation. Our low meltwater simulations suggest that the magnitude of climate responses are strongly dependent on the applied meltwater amount. These highlight the importance of, firstly, constraining projections of Antarctic ice sheet and ice shelf melt, and secondly, of representing Antarctic meltwater in coupled climate model simulations, both of which are important to better project global surface climate changes over the 21st century.
You have time for questions?
Felicity.
Yeah, very hard. Thanks for that. That was really excellent. I'm interested to hear your thoughts, I guess, sparked by conversation I had yesterday about what the impact you would see on warming if the meltwater was injected lower down in the ocean.
Yes. Yeah. Shall I repeat the question? Yep. So Felicity just asked what would be the impact if the fresh water was injected lower down rather than at the surface. So it's a good question because the ice shelf cavities are not at the surface. I think for some of the surface impacts, there's not a large difference, but I think for circulation around the Antarctic margins and the subsurface, it could be quite important. There is a study where they've looked at that, and I can't remember the key details, but I think you'd still get a lot of the surface cooling and sea ice growth regardless. I think Dietmar had a question.
Yeah, I had a question.
Okay. So Dietmar asked about changes in sea level associated with the warming in the subsurface and the cooling. So I haven't looked at sea level in these runs, and I think the main contribution from Antarctic melt on sea level is because of the extra amount of water. I don't know about the thermosteric changes, whether because you've only got a thin layer that's cooling and a thick, most of the ocean is warming, I guess that would increase sea levels, but I haven't looked at it and I don't. Yeah. And yeah.
Are you proposing to directly model Antarctic ice sheets?
I think that will be discussed a lot over the next 2 days. Oh, okay. Shall I repeat that, or can people see it? Yep. I'm not sure if the two are, I'm sure they are a little bit related. So the reduced sea ice loss, so over the 21st century, it's warming and so sea ice is lost. And then we have an anomalous cooling in our meltwater runs, and so we have a reduction in sea ice loss. Separately, when we have the strong surface freshening, we have a reduction in dense water formation. So that's reducing the Antarctic bottom water formation. I guess how sea ice would affect that, probably the reduction in sea ice loss would slightly delay the shutdown of Antarctic bottom water formation, but I know they're written there together in the same point based on geographic setting, but they're not, I haven't actually linked the processes together. Oh, yep. Ben, do you want to go ahead and ask your question?
Yeah, hi. It's an important study, so thanks for giving the talk today. It was nice to see it. I've just asked, I had a question about the carving and how you treated the meltwater from iceberg. I kind of missed the point a little bit, but is that put in as a separate freshwater flux?
So this is just a really idealized study. And so that I've just added liquid fresh water into the ocean model component. And so adjacent to the coast with a 3-2-1 tapering in the Ross, Amazon, Bellingshausen, and West, and then spread north to 64 degrees to represent the drift of icebergs, but there's no latent heat flux. And so it's purely liquid water without those sorts of effects.
Yeah, and did you get a sense about, sorry to ask another follow-up question since I've got the microphone, but the amount of fresh water going into the ocean for present days, I would say fairly high, probably about 30% too high, maybe even 50%. Did you get a sense when you're running the future projections where the threshold on the breakdown of bottom water was in terms of that extra fresh water added?
So it happened around 2060 in our high meltwater ensemble. When we're adding the freshwater linearly, it's idealized. I could go back and check about how much water that was, but I can't tell you off the top of my head.
Yeah, okay, I'll send you an email. Thanks.
Yeah, thank you.
Thank you. Why would change the slide? The last question. Nathan?
Nathan Bindoff. Look, that was great. Can you tell me whether all of the responses I was seeing outside of the shelf area can be just thought of as increased stratification by that freshwater load?
Over the Southern Ocean, yes, but further north, no. So I think Southern Ocean, like for the stratification, you've got to have the cool water at the surface and the warm water at depth. But once you change that, it's more, I guess, infection of the anomalies.
Yeah, so in the real planet, the addition of Greenland in the northern hemisphere would actually counteract a lot of the response that you've actually shown from the purely Southern Ocean.
So there's a lot less ice in Greenland. So we've actually run a third ensemble of runs, which I'll be happy to talk to you about later. But if you compare the high meltwater ensemble to like a high melt of Greenland, there's less water there. So it does have an effect, but not as much as Antarctica. Yeah.
Thanks, Ariaan. You can